All right, guys, we're back at it again. 11.5. Okay, so now with gases, we're going to discuss the relationship between temperature and pressure. So we have a relationship between volume and pressure in Boyle's law. We've got a relationship between temperature and volume in Charles' law. Now we've got a relationship between temperature and pressure under Gay-Lussac's law. All right, I know it's a lot, but we got to keep them straight. This is why we use formula sheets. This is why we write it all down and make sure we're all squared away. So let me get my handy pen all set. Now, if you hear some ruffling in the background, that would be some certain people in my household who remain nameless. You guys can say hi, though. Let's say hi.
Hi. Hi.
All right, there we go. Good. All right. They're totally embarrassed, and that made my day. All right, so learning goal. When the Kelvin temperature of a gas is doubled at a constant volume and amount of gas, the pressure also doubles. Okay, so what do we call that? What kind of relationship is that? Is it indirect or is it direct? Is it indirect or is it direct? Well, if one is going up and the other is going up, that is a direct relationship. All right. So, Gay-Lussac's law states that pressure of a gas is directly related to the temperature when volume and moles are constant. Okay, remember, we're putting all these qualifying statements in, like when volume and moles are constant, or when temperature and moles are constant, or when pressure and moles are constant. All right, so we've got these qualifying statements. Okay, so if the pressure increases, therefore the temperature is going to increase. Cool. That actually makes sense. And if you think about it, if we're talking about molecules, these molecules are at one temperature and they're just chillaxing and they're all good. Now we increase the temperature and they get all excited and they start bouncing around all over the place, and that's going to make the pressure go up. All right. So if we look at Gay-Lussac's law as a direct relationship between temperature and pressure, P1 over T1 equals P2 over T2. Well, where do we see that? Well, Charles' law, that's weird. It was V1 over T1 and V2 over T2. I wonder if that's going to come back to us here in a little bit. Maybe not in this section, but it wouldn't surprise me if we talked about it in the combined gas laws. It'll be really exciting. I know you guys can't wait. All right. So this, of course, is qualified with no change in moles and volume. All temperatures used in gas law calculations must be converted to, that's right, Kelvin. We know that we must have a Kelvin temperature. So the equation for Gay-Lussac's laws can be arranged to solve for any factor. Again, basic algebra, man, we got to hit that hard. Since we have division over here, we are going to have to use multiplication to each side to rearrange this. So to obtain P2, I love how it's go, P1 over T1 equals P2 over T2. Thus, P1 over T2 equals, P1 over T2 over T1 equals P2 alone. Because remember, T2 over here is down on the bottom. We don't want them down on the bottom because that won't leave us P1 or P2 over here. So we got to bring them up top. Got to bring them up top to the other side. It's just like multiplying both sides by T2 because it'll slash them out. So a gas has a pressure of 2 atmospheres at 18 degrees Celsius. What is the new temperature or new pressure when the temperature is 62 degrees Celsius? Remember, volume and moles are constant. Okay, so we need 3 steps to this, right? So the first thing we got to do is organize. Step 1 is we're going to organize our data. So it goes conditions 1, conditions 2, pressure 1, 2 atmosphere, temperature 18 degrees Celsius. We had that's 273 degrees to get our Kelvin conversion. And then we don't know what the second pressure is, so we just put a little question mark, leave it blank. I don't know. But then we have to take our 62 degrees Celsius they want to know, add that to 273 Kelvin. That gives us this 335 Kelvin. With this information, can we figure out what P2 is? Well, of course we can. All right. But we need our root formula, so we got to solve for P2, which we already did earlier. But again, multiplying both sides by T2, getting T2 to cancel out. and leaving P2 all by its lonesome, and then rewritten as P2 equals P1 times T2 over T1. Then it's plug and chug, guys. Nothing more than that. We take our 2 atmospheres, we multiply it by our 335 Kelvin, and put it over our 291 Kelvin. All right? Then that is going to be 2.3 atmosphere. Well, does that make sense? Well, our temperature increased. Yeah. And we know that there's a relationship between temperature and pressure. So if temperature increased, our pressure should increase. But we started at 2 atmospheres. Now we're at 2.3. Yeah, okay, that makes sense. Anytime we do calculations, we always want to go, does it make sense? All right, so good with that. So remember, using gas laws to complete with either increase or decrease. All right. Well, we're start looking for keywords. All right, so we know the relationship is direct. So if one increases, the other increases. If one decreases, the other decreases. All right, so pressure when temperature decreases. Well, hey, it's direct. Okay, so when temperature decreases, well, that's going to decrease as well. So pressure when temperature changes for that should be 12 degrees Celsius to 24 degrees Celsius, because that is a typo. All right, so ignore that, and we're going to go degrees C. All right, so when temperature increases, pressure is going to increase. When temperature decreases, it is going to decrease. So let's check ourselves out. Decrease, decrease, increase, and decrease. Remember, type O, that should be degrees Celsius. So, learning check. Yes, is a pressure of 0.75 atmospheres at 128 degrees Celsius. What's temperature in Celsius if the pressure increases 1.5 atmospheres? All right, well, we know it's going to increase because we have that direct relationship. And notice that the atmospheres double, okay? So let's see. First thing we have to do is convert that 128C. Well, first thing we do is organize, right? Organize the data. But I am curious that the pressure doubles. I'm curious what the temperature is going to do based on this relationship. So at 128 degrees Celsius, we're at 401 Kelvin, okay? We're at 401 Kelvin. So let's take a look. We need to rearrange our formula. Simple enough, right? So what they did here, okay, so they said P1 over T1 equals P2 over T2, or P1 times temperature, the second temperature, equals P2 times T1. Now, why did they do this? Well, they really wanted to get T2 by itself. They wanted to make it kind of easier. So we're going to divide by P1 on both sides, and you'll see here that it cancels out, leaving us with only T2, which it equals P2 times T1 over P1, right? Now it's plug and chug, All right, so if we look at this, we've got 1.5 atmosphere, that's the increased atmosphere, times 401 Kelvin divided by 0.75 atmosphere. Now look at this. 802 Kelvin. Well, what was our original Kelvin? 401. Holy smokes, it is a direct relationship. Since our pressure doubled, what happened to our temperature? It doubled as well. All right? Pretty interesting stuff, right? It's a direct relationship. And this is also why we use Kelvin, because Kelvin works well like that. That was a horrible explanation, but whatever. So let's talk about vapor pressure and boiling point. And perhaps Lisa can do this in the lab with you. You know, boiling point of different liquids really is very dependent on atmospheric conditions. This is why there are a second set of instructions for high altitude cooking of materials, because the boiling point actually goes down. So the question becomes to you, or I pose to you, is can I make water boil at room temperature? Think about it. The reality is, yes, I can make water boil at room temperature. How I can do that is by decreasing the pressure surrounding the water, and it will vaporize at room temperature. So if I take a bell jar, and this is what maybe, like I said, maybe you guys can ask Lisa to do this, like mad science and stuff. Take a container of water and you put it underneath the bell jar and you pull the vacuum. And you can actually find this on YouTube, which say water boiling at room temperature. Or maybe I'll throw up a link on Sakai too, but it's cooler if you see it in person. Anyway, as you draw that pressure away, the boiling point of water is actually decreased, and as it's decreased, the temperature that it boils decreases. All right. So right here is a whole list of, depending on the pressure, what temperature will water boil. So we know that 0 degrees Celsius is actually the freezing point of water. Well, at 5 millimeters of mercury, water will boil at the freezing point of water. Oh my gosh, mind's blown, right? Well, why is that? Well, the reason being is because if I decrease the pressure, the boiling point actually decreases, but guess what? The freezing point decreases as well. Direct relationships. Okay. Yeah. An autoclave used to sterilize equipment attains temperature higher than 100 degrees Celsius, which we know is the boiling point of water, increasing the pressure and increasing the temperature. All right. So that is now Gay-Lussac's law. All right. So we're seeing all these relationships. Guess what's up next? Combined gas laws, putting it all together.